Okay, hello and welcome to day 7 of Advent of Code. What we got today? The treachery of whales. A giant whale has decided your submarine is its next meal, and it's much faster than you are. There's nowhere to run. Suddenly, a swarm of crabs, each in its own tiny submarine, it's too deep for them otherwise, zooms in to rescue you. They seem to be preparing to blast a hole in the ocean floor. Sensors indicate a massive underground cave system just beyond where they're aiming. The crab submarines all need to be aligned before they'll have enough power to blast a large enough hole for your submarine to get through. However, it doesn't look like they'll be aligned before the whale catches you. Maybe you can help. There's one major catch: crab submarines can only move horizontally. You quickly make a list of the horizontal position of each crab. That's going to be a puzzle input. Crab submarines have limited fuel, so you need to find a way to make all of their horizontal positions match while requiring them to spend as little fuel as possible. For example, consider the following horizontal positions. This means there's a crab with a horizontal position 16, a crab with horizontal position 1, and so on. Each change of one step in horizontal position of a single crab costs 1 fuel. You could choose any horizontal position to align them all on, but the one that costs the least fuel is horizontal position 2. To move from 16 to 2 is 14 fuel. Okay. To move them to that position. This costs a total of 37 fuel. This is the cheapest possible outcome. More expensive outcomes include aligning at position 1. Oh, I see. Position 3 or position 10. Determine the horizontal position that the crabs can align to using the least fuel possible. And let's have a look at our puzzle input. Right. So let's think about this for a bit. You know, the quickest way is to just do an iterative approach where we go through. This seems too simple at first glance. So let's do our read puzzle input. That's going to be our input day 7. We're going to have our input count and our input values, and then I'm just going to do a scan integer comma list, because that's what that is. So let's create this. Oh yeah, sorry, let me go to this view. I did create a new file called platform.h just to define the various different types of signed and unsigned integer widths. So our count is going to be a U64, that's an unsigned integer of 64 bits long. So that's going to be our input count, starts off as 0, and then our input values. If I come back to our puzzle input, you know, the biggest never really gets bigger than 1,000 or so. So I'm sure and we never get negative numbers, so I'm sure U16 is more than enough for that. So that's our input values. of day 7 max input values. We don't have any more than 1,000, I don't think. Just to be sure, let me make that 10,000. So this would call did we read it? And if we did read it, I just want to printf. This is day 7. We read values. So input count. So let's get our puzzle input. There it is, input day 7, and let's copy and paste the example input to begin with. Let me open that in here, and then open day 7 here, compile. There we go. So we read 10 values, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so it's going to be, basically we need to go through each value. Again, let me get this. So we need to go through each value. So here n equals 10, and then for each value we need to basically subtract it from our desired position to get our fuel. So depending on the number of positions as well, move from 16 to 2, 1 to 2. Yeah, depending on our I think our complexity just becomes n times n. We can kind of help reduce that by you know, we have some duplicates, so we could use our bin, you know, putting things into various value bin strategy. That might be a way to do it. So let's do this the easy way first. So the way to do that would be to I equals 0, I is less than input count. Let me do this. Nah, should it be 64, I guess. So our value is input values I, and then we then need to loop over so we'll call this K. So this would be the inefficient way of doing it. I'll do like target precision equals input values K, and then basically we do fuel to shift is just our value minus our target position. Let me cost a total of 37 fuel. This is the cheapest possible outcome. So our fuel sum equals 0. Our fuel sum plus equals our fuel to shift. And then we kind of need to say, like, once we've got our fuel sum, we then need like a smallest fuel so that will just set it to the maximum number, and then we'll check like if our fuel sum is less than our smallest fuel amount, then we'll set our smallest fuel amount to our fuel sum. And we'll also have a U16 our most efficient position. We don't know what that is yet. Am I spelling efficient right? How do you spell efficient? It's F-I-C-I. And then we will say our most efficient position is equal to our... No, I'm going to swap this around. So we've got our target position here. This is our value. And then we'll just print that. So this is day 7. Most efficient position is using fuel. And that will be our most efficient position and our smallest fuel amount. So let's compile this, run it. Most efficient position is 2 using free fuel. Is that correct? No, it says it costs a total of 37 fuel. I think we also want to say, like, if I equals k, we just continue. So we don't want to compare the same place. Why does that say oh, we also need to account for, so we need to use the abs, which I think is the absolute function. So if this is negative, we actually want it to be positive. And to do that, it's just abs. Just abs in standard lib. That's saying 23 fuel. Still incorrect. Yeah. Where's my logic going wrong? Let's do the good old printeroo. I want percentage u minus percentage u equals percentage u. So I want value, or rather I want abs. Zero. So our target position first is 16. Then we do 16, 0, 1, 0, 2. Is our input being read correctly? That's the next thing to ask. Printf percentage u. No, it's not. And why? I think our scan integer comma list just expects I16. If I go to input helper, just expects int, which is I6. Right. So that just becomes D. Yeah, it was an issue with our reading. So I want to make sure that for integers, if these are going to be reusable, maybe a 32 is a bit more future proof. 16120, and then now when I look at yeah, most efficient position is 2 using 37 fuel, and I reckon if I re-enable this where we continue when the two indices are the same, we should get the same answer. Yeah. So that's working. Let me just get rid of this now. So these now need to be I32. Still works. Yeah. Okay. So I could do this with the puzzle input. And it's going to be, let's have a look. Save that. I am going to comment all you out. And just see how many values we read. 1,000. So it's going to be doing 1,000 times 1,000 operations, which isn't that bad for now. It's slow because I'm printing so much. Maybe I shouldn't print it every line. Yeah, let me disable my line printing thing. End task. So if I now compile, run it, most efficient is position 779 using 105 fuel. How much fuel did they spend to align with that position? What did it say, 105? Is that correct? Oh. Come on. Oh no. Advent of code is down. Okay. 105. There we, oh, that's not the right answer. Your answer is too low. Interesting. Because when I did this, most efficient position is 2 using 37 fuel, which is correct. Precision 779 using 105 fuel. Is that because we actually need to you could choose any horizontal position to align them all on. What I don't, so what's ambiguous to me at the moment is, am I trying to align them to one of these positions, Or, for example, could I align them on position 11, even though that's not a position listed? And it looks like I could. This means there's a grab. Each change of one step, you could choose any horizontal position to align them all on. So obviously, the most efficient position will be somewhere so I mean, there would be a way to think about this more cleverly, mathematically. We could just look at what's the most common number. 2 is the most common number. But then, even if 2 was the most common number, even if there were, say, let me get rid of the puzzle input again and get our. And I'm gonna align these, so order them 2, 2, 2. There's 3 2s. There's a 4. There's a 14 and a 16. And I'm gonna simplify this. 0, 0, 0. We're gonna have 2 zeros, 3 2s, and 16. So let's run it. Obviously, most efficient position is 2 using 18 fuel. Now, if I bump this up to 216, is it always going to be the most common one? Like, even if I have like 2 massive numbers, is it always just going to be the most common number? And why is that true? How do I prove that? Because these will always return 0 for fuel, the most common number. I guess there's still these 2 numbers. So if I was to get rid of the zeros, or rather 2 zeros, 3 2s, and then maybe say like 4 different but big numbers, it's still 2. Like, at what point does it become? So now it's saying most efficient position is 100. So what happens if we, let's take the average, let's compute the average. So compute average. So that's pretty simple. We just need to do like our sum. So we're going to do sum plus equals our input values I, and then our sum will divide by, you know what, this is going to be a float, so it can be a decimal number, and then we're going to divide it by input count, and then we'll do printf average equals %f, this AVG for average. So at the moment our average is 1,285, and our closest number would be this one. And now if we got rid of that one, I'm not sure our average helps. Again, if I reorder this so it's in ascending order, our median, how many values are there? 10 values. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3. So these are our two median values. And the average is 782. If I was to insert a 1 here, we would then have 1, 2, 3, 5. Our 2 would still be 2. And if we were to insert 5001 here, it's now 100. And if I was to insert 99 here, it's now 99. Ugh. Is that always true? I have a feeling it's something to do with the median, but I'm not sure how to prove why. In which case, our formula would just be like, if I make this 50 now, it's now 50. Is it always the first of our medians? Like, if I made you 98, now it's 99. Basically, I want to find an example. So at the moment, 99 is our median. Can I create an example of these that will break 99? And that's just if I say I make you 98, 98, 98, 98. Still 98. But if I add another 98 and another 100 here, so 99 still is the median. Like, at what point I guess Yeah, because I always have to keep 99 as a median, I always sort of have to balance the other side. And if I was to make these much bigger, one, two, three, four, five, six, seven, 8. 1, 2, 3, 4, 5, 6, 7. Oh, is that not 1, 2, 3, 4, 5, 6, 7, 8? 2, 3, 4, 5, 6, 7. So it's actually not quite balanced. Okay. I think that's it. So I'm going to, you know, we have to sort the values. We have to find the median and then compute the fuel cost. That's basically what we have to do. So first up, sort. Let's have a look here. Sort. How do we sort? Show me. No, I just want to just. Yeah, blah blah. The standard C library provides qsort, which can be used for sorting your array. Oh my god, this website. Qsort takes our base. The parameters are base address of the array, size of the array, and pointer to comparator function. So qsort and the comparison function. So here we go. I'm going to call this qsort. I think that's going to put it in ascending order. If we're doing A minus B. So to sort the values, it's qsort. We give it our input values, our input count, our size of i32, and our qsort sending. And then let's print it. Printer. So let me get rid of you. Let's get our example code. And let's compile it. 4, 7, 14. So that's sorted that nicely in ascending order. And then to find the median, it's just the, like, it's pretty much just input count divided by 2. So our median index is this, and we also need to check if our input count, we need to check if the size of our array is odd or even. If it's even, then I think we're going to have two median numbers. And we're going to have to check both of them, I think. But if it's odd, we're going to have one median number. So the way to check if this is even is just to modulo it by 2 and check if it equals 0. So this is the even case. Else odd case. So the odd case is the simple case. So again, I'm going to printf so that's going to be our input values median if there's two medians, it probably means we need to check all the possible values from median 1 to median 2. I've just realised. That's probably why our puzzle input, or proper puzzle input, didn't work. In which case, I'm going to say medians equals percentage d, so that's going to be median I plus 1, so sorted values. So let's see. So medians 2 and 4. And then basically we're going to do compute the fuel cost. So I'm going to hoist, oh wait, new into like int day 7 get fuel cost. So that's going to require our, let's have a look. Input values, and I use 64. Input count. And we're also going to need a range. So I'm going to say like x begin and x end. So we start at x begin. And then we finish at x end. So this actually becomes our target position. we want to return multiple values from this, so I'm going to do it as a structure. So it returns U. So it's going to have our U16 fuel cost and U6 I32 position. So I'm going to copy U. Here's our result. Our result dot fuel cost is going to equal to our result dot position is going to equal to 0. And then basically we'll say if our fuel sum is less than our result dot fuel cost, then our result dot fuel cost is equal to that, and our result dot position equals that, and then we'll return results. And then we'll basically do so our x begin is equal to input values median I, our x end is input values median I plus 1, so we can do that there. And here, x begin, x end, our input values and our input count. And then our struct day 7. So our results is equal to this. And then I'm going to get you is our results dot position and our results dot fuel cost. So if our target position I'm going to get is equal to our value, and we continue. So our most efficient position is 2 using 37 fuel. Actually, we want this to be greater, less than, or equal to x end. Which means what we can then do is actually move these up here. And set these to 0 to begin with. And then the odd case, x begin is equal to x end, which is equal to our input values median I. And then this can go ha. fuel. So that still works. That means it's 2 and 4. If we were to add another, say like another 14 here, our median is 2. I'm going to make it a 1. 3 1s, 3 2s. If we were to add 2, another 1. A most efficient position. And there's a way to validate this actually. And that's simply to do like 0 to 16. So if we check all possible values, so using the inefficient method, most efficient position is 2 using 39 fuel. Let me just add way more ones. Most efficient position is 1 using 41 fuel. Okay. So comment you up. So now let us go back to our puzzle input, copy you, and delete you, paste you, save you, and run it. So it gives us 2 medians, 376, 379. The most efficient position is 376 using 25,027. Sorry. Yeah, 25,027 fuel. Ha! That's not the right answer. Your answer's too low. It's entirely possible my theory is wrong. About using the median. $376. And if I did my inefficient method of 0 to 1859, I get a completely different result. I guess this just needs to be we know what the max value is by input count, the last, so that should still work. But that's not the right answer either. What am I doing completely horribly wrong? Okay, we need to read this again. Each change of 1 step in horizontal position of a single crab costs 1 fuel. And then if I look at my I'm going through all the target positions, so I'm going from 0 to whatever the max value is to 1859, and then looping over each value in the array. I'm checking how much fuel it is to shift by doing value minus target position, abs, loop, then adding that to the sum. And if the sum is less than our previous fuel cost, so it's cheaper, we cache it, and we also cache what that position was that we're moving all of them to. And if target position is just the same as our value, i.e. this minus this would equal 0, we just don't do this bit. I mean, I don't see how that would... Yeah, we get the exact same answer. I mean, this feels wrong, doesn't it? Most efficient position is 1735 using 69 fuel. Why? Why? Yeah, that's obviously wrong. Because what about all these values? K equals 0, K is less than input count. Input values, value, fuel to shift. Checking position, percentage D. Checking bus 376, fuel cost 27. Checking bus 0377, 0378, 0379. I'm just going to comment new out as well. And then the inefficient way. Some of them are 241. So where did this 69 come from? Ah. That just looks so out of place. Alright, I'm going to look at 1735. 1735. 1735. And then I want to print here. And then I'm going to do a couple of tabs, and then it's going to be value and fuel. So again, we're going to have our value and we're going to have our fuel to shift. See, it's like, should be way more than 69. Which means we're getting an overflow. Our fuel sum just isn't big enough. Yeah, I should have known. Should have known. So I'll use a U64 for our fuel sum. Same here for our fuel cost. There should be a U64. So our fuel to shift, I'm gonna do a 64 here. This will be U, this will be U. That's still percentage D. So let's compile that, run it. Go all the way down to the bottom. So yeah, you can see the fuel cost is in the million range. This is saying most efficient position is 0. Why? Oh, because now our fuel cost should be this, right? C in types. There is a how do I get like the C long max value, integer limits.h. I think I want a UL long max, which is in limits.h. So this is going to go in our platform file. Include limits.h, and then I'm just going to type def max u64. Oh, I guess it'll be a define, sorry. Because that's a numeric constant. So let me just go all the way down. Yeah. So we got our inefficient method, which would be input values, input count -1. And then we got our theoretically more efficient method, this should be I64U, I64U, and then I'm not going to print these anymore, because that's just gonna, that I'm gonna comment out for now, just in case. So run it. So our two approaches are returning the exact same result, which is very promising. So let me copy you, and let's give this a go. Oh, finally! Got the right answer. Let's see, what part 2? The crabs don't seem interested in your proposed solution. Perhaps you misunderstand crab engineering. Yeah, I very much misunderstood it. As it turns out, crab submarine engines don't burn fuel at a constant rate. Instead, each change of one step in horizontal position costs one more unit of fuel than the last. The first step costs 1, the second step costs 2. As each crab moves, moving further becomes more expensive. This changes the best horizontal position to align them all on. So isn't that just 2 to the power of how many steps we move? So for example, move 1 to 5 equals 10 fuel. Oh no, it's not, because it's not doubling, it's only increasing by 1. So that's like a triangle. Is that triangular number? Triangular number, yeah. One, 3, 6, 10, 15, 21. 1, 3, 6, 10. Oh. And I don't know if there's any like easier way to compute triangular numbers than to just do the loop. Triangular numbers are given by the following explicit formulas. So the triangular number for k is just the sum of all numbers up to from 1 to k. In which case, yeah. So the best way to do this then would be to after we sort the values, we're now going to construct a table of triangular numbers, because each one increments from the last 1, 2, 3, 4. But like the fuel cost is the sum of all those increments, so yeah. So the way to do this is for I equals 1, and we know we're going up to the highest value, which we already know because we've sorted the array. Input values, input count -1. It's going to be the last value in the array, which is the highest. I++. We're going to have a running sum, starts at 1, and we're going to have a triangular numbers table, which I'm gonna malloc this. And it's going to be whatever our max value. Let me store this. Our array of input values is I32, so our max input value is equal to this. So it's equal to max input value times size of U64. And then we need to remember to free it. And then our triangular numbers I -1, because we're starting from 1. Nah, I don't like doing it this way. I want to start from 0 up until the highest number is equal to our running sum. So it's the same, actually, yeah. Our running sum starts at 0. And then our running sum, we're just going to add I+1. And then just to validate this, I want to printf our triangular number, which is going to be our running sum. But I don't want to do all of them, do I? Because that's a lot. Oh yeah, initialization of a cast. I forgot to make this a pointer. Wait, what's that saying? Triangular. Say what now? Oh, if I need to put that into our did read function. So these will grow rapidly. Not as rapidly as a factorial, at least. But, interesting that it halted. Because that needs to be +1. There we go. So we now have our sort of table of triangle numbers, which we can use as a lookup. So this will also take in our triangular numbers. And then when computing the fuel to shift, it's just, we just index into that array as a lookup. That's the main change here. So let me get rid of this line. And now let me get you. You should really be in here. So we can toggle between using the median and the non-median method. So if day 7 use median method, actually then this can just be an else. And this is our brute method. Triangular numbers. In which case that goes there if we use the median method. So compile, run. Median method. Most efficient position is 379. Is that different? Yeah, puzzle answer was 35. Oh, we should validate this with the example given. And also, it might break our median theory. Let's give it a go. So it's saying most efficient position is 4 using 170 fuel. But it's actually saying 168, so it's obviously wrong. Close though, 170. Whereas if we were to use the non-median method, that's correct. Most efficient precision is 5 using 168 fuel. So yeah. Yeah, I'd love to know the maths behind it, but that little median trick only works. Which does it intuitively make sense? It made sense when it was linear. Yeah, that would require like a more stricter mathematical proof to figure out why you can't use the median method. But at least, well, let's check it actually works for the real input first. So saying most efficient position is 490 using that fuel. It's a number. It's a number, Wang. Yes, we did it. Well, I did it. But you know, you were there in spirit. Cool. Looking forward to day 8. Thank you so much for watching.